Welcome back to Very Ordinary Differential Equations. In this lecture, we study more applications of first-order equations, specifically mixing substances in a single tank. So suppose you have a single large mixing tank. We're going to presume that inside the tank, the substance that we're putting in is always evenly mixed. We don't have like more concentration at the top and less at the bottom or anything like that. Even as we add or drain substances within the tank, it's a uniform concentration. So for example, maybe we have a 1,000 liter tank and it's full of pure water. But a solution of 4% salt water is pumped in at a rate of 100 liters per minute. Contents are drained out at an equal rate so that the volume inside the tank is always 1,000 liters. So we start with pure water and we begin pumping in salt water at a fixed constant rate. What's the salt concentration inside the tank at a given time? Similar problems can be phrased with other mixtures of other different chemicals. Now, looking ahead, you might have multiple tanks and multiple different substances, but that will generate a system of differential equations. Hold your horses, we'll get there quite a bit later in the course. For now, a single tank with a single substance. One thing that's worth observing, it's generally much easier not to track the concentration of the material, but rather the raw amount. Okay? We'll see why when we get to solving the differential equations. Let's use P for proportion instead of C for concentration, because typically we use C for constants. So we're going to let A represent the amount of the substance we have, and P to be its proportion. Certainly, the proportion is simply the amount divided by the total volume. Okay, so the two things, proportion versus amount, are not really that different. So the differential equations to govern the model, they're more easy to set up in terms of A prime rather than P prime, but there's an obvious relation between the two since the volume is constant. Now in the previous problem, we had 100 liters of 4% salt being pumped in per minute. So how much salt is being added per minute? Forget the concentration or the proportion and just ask amount. If it's 100 liters at 4%, there are 4 units of salt being added per minute. Meanwhile, 100 liters are being drained, but the concentration in the tank is the amount of salt in the tank divided by 1,000 because it was a 1,000 liter tank. Okay, so 100 liters are being drained, but the concentration is A over 1,000. 100 liters times A over 1,000 gives A over 10 units of salt being lost every minute. So we've converted into amount rather than proportion. There are 4 units of salt being added per minute and A over 10 being lost every minute. So we're gaining 4 units of salt per minute and losing A over 10 units of salt per minute. This gives us a pretty straightforward differential equation. The rate at which our salt is changing, well, we're gaining 4, so plus 4, and we're losing A over 10, so minus A over 10. It doesn't take a lot of work to change this into a first-order differential equation, A prime plus A over 10 equals 4. The homogeneous version of this, A prime plus A over 10 equals 0, definitely has a solution of e to the negative t over 10. Then you just need to find a single solution to the inhomogeneous equation. Notice that if A is 40, then A prime is 0. If A is constant, then its derivative is 0, and I would end up with 0 plus 4 equals 4. So we quickly find not just a single solution to the complementary equation, but also a single solution to the inhomogeneous equation given here. So we can represent all of our solutions by 40, the one particular solution to the inhomogeneous equation, plus some constant times the solution to the complementary equation, so C1 times e to the negative t over 10. Now we can divide the amount A of t by the fixed volume of 1,000 liters and get the proportion at time t, or the concentration of salt at time t, is given by 4% plus some constant times e to the minus t over 10. And there's an obvious relation between constants. This new constant is just the old one over 1,000, but hey, it's just still a constant, so we're just going to write it as a new constant. So here's our solution. The concentration at time t is 4% plus something times e to the minus t over 10. We had an initial condition in our problem that the concentration at time 0 was 0. We began with pure water. So plugging in t equals 0 will make this just equal to 1, but this will be 0, and we can solve that this constant C2 needs to be negative 0.04. Therefore, we can plug in negative 0.04 for C2, factor out the 0.04, and say the concentration at time t is 4% times 1 minus e to the minus t over 10. Now this solution has a steady state. As t goes to infinity, p simply tends to 0.04. That represents if the tank was already at 4% salt, what's flowing in is exactly the same as what's flowing out, and our constant solution is maintained. Observe back at the beginning, regardless of the value of C2. As t goes to infinity, this exponential term will drop to 0. So 4% is always the steady state solution, no matter what our initial conditions were. And this makes sense, whether we start with pure water, super concentrated salt, or anything in between. If the water flowing in is at 4% salt and it's draining out at the same rate, eventually it's going to even out. As time goes to infinity, the inflow will eventually swamp whatever initial conditions we had. So as time goes to infinity, the tank will approach 4% solution. Now we can do the same problem again, just by leaving all terms really general, not specifying any actual values, just leaving them as unknown constants. So our volume is capital V. We begin with a solution at concentration P sub 0. A solution of concentration P flows in at a flow rate of F, while solution flows out at the same rate. Determine the concentration at time t. Same setup as before. Tank full of something, stuff flows in, stuff flows out, solve for concentration at time t. We just haven't specified any actual values. So we're going to convert into amounts rather than concentrations. So what's the amount of material in our tank at the beginning? Its initial concentration, P naught, times its volume V. How does the amount of substance in our tank change? Well, it flows in at a constant rate and it flows out at a rate which depends on the current's concentration. So the change of substance in our tank is given by two terms: flowing in at concentration P and rate F, flowing out at rate F with concentration, current amount over volume. Rearranging this, we get a nice straightforward first order linear differential equation. A prime plus F over V times A equals PF. So here's the differential equation we want to solve. It's pretty quickly solved. The homogeneous version is just definitely going to be e to the negative F over V, and a single inhomogeneous solution will be the constant PV. If I replace A with PV, the V's cancel, and I end up with just PF, but if this is a constant, its derivative is 0. So here's a single inhomogeneous solution. E to the minus Ft over V is our single solution to the complementary equation. So all solutions are given here as the one particular solution plus a constant times the single solution to the homogeneous equation that we found. Our initial condition was that A of 0 is A naught, which was just the initial concentration P naught times V. So coming here and setting t equals 0 makes this 1, allows us to solve for C is A sub 0, which is P0 times V, minus PV. So here is our constant C. It's P naught times V minus P times V. We now have a nice explicit solution right here. The amount of substance in our tank at time t is given by PV plus P naught V minus PV times e to the minus Ft over V. But we were interested in finding our concentration at time t. So we're going to take our amount and divide it by our volume, which actually simplifies things rather nicely. So our concentration, or our proportion at time t, is given by the inflow concentration P plus the difference between our initial concentration and our inflow concentration times this exponential term. Observe a couple of things. As t goes to infinity, since capital F and capital V are actual physical things representing a flow rate and a volume, F over V is positive, so negative Ft over V. As t goes to infinity, e to the negative that is going to go to 0. So our steady state is just given by P. No matter what, the steady state solution is given by the concentration of the inflow. This makes sense again. Also observe how similar this is to Newton's law of cooling. It's actually the same thing, really. Okay, so our concentration at time t is given by some sort of inflow rate plus this difference times an exponential term. But what if the inflow and outflow of our tank are not balanced? For example, I have a 1,000-liter tank, but I don't begin full. I only begin with 300 liters of pure water. I begin pumping in a 3% salt solution at a rate of 20 liters per minute, but I'm only draining stuff out of the tank at a rate of 10 liters per minute. So fundamentally, I am adding liquid to the tank. Eventually, it becomes full, and when that happens, I reduce my inflow. So once the tank is full, then I'm only flowing in at 10 liters per minute while draining out at 10 liters per minute. Can we find the concentration as a function of T? The first order of business is to find when the tank is full, because that's when something fundamental changes in our differential equation. We are gaining 10 liters of liquid per minute. Since we started with 300 liters out of 1,000 liters, we need to gain 700 liters to become full. At 10 liters per minute, it'll take us 70 minutes to do so. So for the first 70 minutes, I have one situation, and then after time t equals 70, the differential equation has to change. Let's actually determine the concentration of the liquid in the tank at this specific moment, t equals 70. Up to 70 minutes, what's happening? Salt water is flowing in at 20 liters of 3%, converting things into amounts rather than concentrations. That is 0.6 units of salt flowing in every minute. But what's flowing out? Well, 10 liters is flowing out, but what's the concentration flowing out? The concentration flowing out is the current amount divided by the current volume. The current amount is what I really want to solve for, but the current volume I actually know quite explicitly. The volume of liquid in the tank began at 300 and was gaining 10 liters per minute. 20 liters flowing in, 10 liters flowing out, we're gaining 10 liters per minute. So for t going from 0 up to 70, 300 plus 10t is the volume of liquid in the tank. The volume of liquid in the tank is actually changing with time. So overall, the amount of substance in the tank is changing. Well, it is gaining 0.6 units at a constant rate, but it is losing this right here. This is what we are losing. I've just canceled out a factor of 10. Also, the initial concentration in the tank was 0 because we did begin with pure water. Moving terms, we have a nice first-order linear differential equation here. So here's the first-order differential equation we want to solve, which will govern the behavior of our tank from time t equals 0 up to time t equals 70. The complementary equation is solved by 1 over 30 plus t. So if we simply replace this 0.6 with a 0 and solve using our existing techniques, it will be solved by 1 over 30 plus t. By variation of parameters, we can then find one solution to the inhomogeneous equation, as this right here, 18t plus 0.3t squared over 30 plus t. So therefore, all solutions are given by this single inhomogeneous equation plus 1 over 30 plus t times some constant. So this c here is for my 1 over 30 plus t times a constant. So this represents all solutions up through time t equals 70, because after time t equals 70, the system fundamentally changes. Here was our solution from time t equals 0 to time t equals 70, but we do have an initial condition. At time t equals 0, the initial amount of substance in the tank is 0. Replacing t equals 0 is pretty easy. We just get c over 30 equals 0. Therefore, c is actually 0. This simplifies things a little bit. For times t up to 70, we have a of t is this equation right here. For time t equals 70, if we just plug in t equals 70, we get the amount of salt in the tank at time 70 is 27.3 units of salt. With a volume of 1,000 liters, that means the concentration is 2.73%. This is relatively sensible. Remember that we were pumping in 3% salt solution. We started with only 30% of the tank full, and we were also draining some as we went. So by the time the tank is full, we're actually pretty close to 3% salt. But what happens after the tank is full? Once time reaches 70 minutes, the inflow gets reduced. So on the one hand, we have a new differential equation to solve. On the other hand, it's actually easier. Past time t equals 70, the volume is going to be constant because inflow and outflow are balanced against each other. So the volume in the tank is going to stay at 1,000 liters. So here's the differential equation we get. How much salt is flowing in? A constant rate of 0.3. Okay, we got this 0.3 earlier. Now how much is flowing out? 10 liters times A over the volume of the tank, which is 1,000. 10 over 1,000 produces just A over 100 here. So we get a pretty simple first order differential equation, and we pretty quickly solve it. Okay, one particular solution is just given by the amount of salt being 30. Otherwise, we do expect an exponential of e to the minus t over 100 just because of this constant 1 over 100 here. We do have an initial condition to meet, however. At time t equals 70, we know that the amount of salt in the tank is 27.3 units. So at time 70, the amount is 27.3. We can use that to solve for c. Now, t not being equal to 0 does mean we're going to round this off, but that's fine. c is approximately negative 5.44. Setting t equals 70, we get e to the minus 7 over 10. A of 70 is 27.3. Works out to be just that, negative 5.44. So here's our solution, which is valid for times 70 and beyond. Altogether, what do we have? We have one function which covers our solution for time up to 70 and another different solution for times past 70. And here it is presented as a piecewise function. For times between 0 and 70, use this. For times 70 and beyond, use that. Now, the way I've written it is slightly ambiguous. At times 70, which one are you supposed to use? But honestly, it doesn't matter. Remember that we plugged time t equals 70 into this first solution to set up initial conditions to solve for this constant right here. At time t equals 70, the two functions agree. It doesn't really matter which one you use. All right, here's our piecewise defined function, but it's giving us the amount of salt at time t, and we're generally more interested in the concentration. So I need to divide each of these by the volume at time t. But remember that the volume at time t was also kind of tricky. For time 70 and beyond, the volume was a constant 1,000 liters, so I'm just going to have to divide this by 1,000. But for time 0 through 70, the amount of liquid in the tank was not constant. It was 300 plus 10t. So that first bit I'm going to have to divide by 300 plus 10t. So here's the proportion of salt in the tank at time t. The first solution for the amount got divided by 300 plus 10t. The second solution for the amount got divided by the constant 1,000. So what have we covered in this lecture? When studying substances mixing in a single tank, we usually want to set up equations in terms of amounts rather than concentration. It's pretty easy to go back and forth between the two, but the differential equations are a little easier to set up in terms of amounts, and then back convert into proportions once you have the solution. So just compute inflow versus outflow and derive some sort of linear first-order differential equation. Sometimes you may have the tank fill or empty after some time, and you'll have this cutoff. So these piecewise defined scenarios where the differential equation satisfies one thing up to a given time and a different thing past another time, we'll actually come back to later. For now, however, we're just solving them independently and making sure that the end conditions of one solution match the starting conditions of the other, depending on what time the scenario changes.